Okay, so good morning, everybody. I'm here from Berlin, so it's afternoon in Berlin. I just looking for the pointer. Okay, I have it. So I will give a presentation on some experiments we have been doing in Berlin in our lab in preparation for Bepicolombo Mertis and for the interpretation of messenger data. So this is just the introduction, so you know that for a long time Mercury was thought very similar to the Moon, and because both are small rocky bodies with no exospheres, and Mercury's surface reflects much less sunlight than the Moon, so it's much dark, and so was thought to have iron or titanium as darkening agents. But NASA messenger instrument found out very small amount of iron and virtually no titanium. And while the same messenger data tells us that there is an increase of graphite in some dark regions, and this graphite should be 1 to 3, maybe even more percent higher than the surroundings. And so that's what we did in our lab. We measure reflectance spectra of several phase angles for several phase angles for graphite, from the UV to the thermal infrared, and we are measuring fresh and heated samples because we can heat samples to Mercury surfaces in vacuum. We took reflectance spectra of comatiite because comatiite, as we published some years ago, we consider as a, let's say, standard Mercury. Even it's difficult to standardize a Mercury soil, but we took the comatiite as a mean Mercury, and then we try to mix some graphite to replicate this darker region on Mercury. And we measure emissivity spectra of those graphite and comatiite mixed with graphite from 100 to 400 degrees, so at different insulations on Mercury surface in preparation for Mertis on the ESA Bepicolombo mission. So few words on Mertis, of course. It's a thermal infrared spectrometer collaboration between the University of Münster and DLR in Berlin. And the very important part is this one. So we will measure the surface radiation from very hot Mercury in the 7 to 14 micron range, and of course there was no comparable instrument of the NASA messenger mission, and so Mertis will open a new data set of data that will be then very useful for the interpretation of the surface composition of Mercury. And so these are just in brief. I will not spend so much time on this, but of course we will study the Mercury's surface composition in the thermal infrared, and we have a map of the mineralogy of Mercury. This is Mertis. So this one is Mertis on the spacecraft, and you may see that it was integrated many years ago, so 5 years ago almost, and finally October this year Bepicolombo is gonna start. So finally we're gonna start our journey to Mercury. And spectral measurement at the lab. So I think many of you already heard about the laboratory. So we have 1 and 2 spectrometer working in parallel, and especially this spectrometer is attached to a chamber, that is this chamber here, and the chamber can be evacuated, and we can put many samples in the chamber and measure them at very high temperature. And the very nice part of this laboratory is that it's very flexible, so you can accommodate your experiment inside. You can do a lot of things among them. For example, you can mount Mertis. This is Mertis mounted on the chamber because we have a window here transparent in the infrared, and you see a very happy PI looking at his baby, let's say. And with this method, we could take measurements of some hot surfaces replacing Mercury with Mertis. So the overview of PSL, I will not spend so many words on that, but you know we can measure emissivity, reflectance, and transmittance in a very wide spectral range. So what we did in the lab is we measured reflectance from the UV visible to the thermal infrared. So this is our komatiite. So let's say this is our standard mercury at different phase angles, as you can see. So you see even the difference of the reflected light varying with the phase angle. And then we measured the graphite. So as already mentioned before, graphite is very flat, even in the visible, but in the infrared spectral range too. So this is reflectance of graphite. And if you think about the komatiite mixed with some graphite, so this is the komatiite with few percent of graphite. So I can switch back and forth, and you may see the effect of graphite on the komatiite, that it's darkening and flattening the reflectance spectra. The same thing we have been doing on the heated sample, because after we measure emissivity, we have our sample that has been thermally processed to 400, 500 degrees, and so we always try to measure them back in reflectance to see what happened to those materials, especially after being exposed to this very high temperature. So this is our komatiite at 0.25 microns. You may see that there are some important changes that we already published a few years ago on measuring reflectance on a heated or not heated standard for mercury. This is the graphite, again, very flat and not so many spectral features, even in the thermal infrared, where we are very interested. And again, komatiite mixed with graphite, you may see the effect of graphite on komatiite. So from this point of view, we may see a change in the komatiite spectra due to the small amount of graphite, and even very few percent of graphite bring this very high degree of spectral changes. This is very, very interesting. And maybe, oops, sorry. Can you see my presentation?
No.
Oh, okay. I should.
It went away.
It went away. Can you load it again?
We'll bring it back.
Okay, so I guess yeah, this is the beginning of the emissivity measurement. So you see our graphite at ambient temperature. You may see this is a webcam mounted in the chamber, so it's very useful to monitor what happens. And I'm gonna go on with a higher and higher temperature, so you may see you reach the 300 degree. If I switch off the light, you may see, well, the cup is heating, of course, to have the surface at 300 degree in vacuum. The cup must be much higher in temperature. This is the 400 degree, and this is the 400 degree without light. So you may see at this temperature we are glowing, we are producing some light in the chamber. Going back to emissivity measurement, so this is komatiite measured for several temperatures on 2 days, and you may see how there is an effect of the temperature on the depth of the bands. You have some band shift and very well known process happening with increases temperature. Something that we did, we measured graphite at different temperature, and you may see we found an interesting. Oh, I don't have my pointer now here. An interesting band around 8 microns, and this band is much more interesting than this, even if it's weaker, because of course this 9 micron band, it's in a region where you have silicate, so you may have many other bands, while the 8 micron band can be quite an important band to detect graphite on mercury. The same band we found here in the graphite, so in the graphite mixed with komatiite. So if we think about this as a dark region on Mercury, we may probably see some spectral feature around 8 microns that can tell us if we have graphite on planet Mercury. Just a last point on the stability of this chromatite and graphite. We have been measuring at several temperatures for many days, and you may see that the spectra tends to repeat themselves. And this is good because this means that after so many days of insulation and the surface has been heating, if we have some spectral features, we're going to find them anyway on Mercury. And you may see that the graphite added to the chromatite brings some in any case, important spectral features in the Christensen feature region, in the Westphalian bands region, and the transparency feature band region. And just to finish, this is a little bit of spoiling the next talk, because there has been a detection or a possible detection at 600 nanometer from Rachel Klima. What we did is we tried to repeat this detection, and so this is our graphite fresh, and I cannot say that we see so much of a 0.6 micron band. We see something more around 500 nanometer. Nevertheless, if we mix chromatite and graphite, and we measure and we make a ratio of this mixture to the chromatite, so following the same procedure that has been used by MDIS, we don't see so much of a band here. We see more some feature around 0.8 micron, but this feature belongs to chromatite, so we don't believe that it's something to do with the graphite. The same thing we did with a heated graphite. So again, we see some hints of a band. You have to see the reflectance scala here. It's really a very fine faint feature. If I plot this on a larger scale, you see really a flat spectrum. So I don't see really some high, a very deep band here. And the same thing we did on the chromatite plus graphite versus the graphite. So if we do a ratio, we don't see any hints of a band around this region, and the same we don't see in the chromatite plus graphite alone. So just to go to the summary and outlook, we made a set of experiments to investigate the detectability of the graphite on the remote sensing observation of the Mercury surface. We have been taking reflectance spectra of graphite, and we know that they are almost featureless. But we have been measuring thermal emissivity spectra of graphite, and we found this 8 micron band feature that give us some confidence that we are confident that maybe we can find this on Mercury, though this could be a possible detection of graphite. And what we even saw is that a very few percent of graphite has a high influence on the reflectance spectra and the emissivity spectra that we measure for pure chromatite, so on what we could think average Mercury or darker regions on Mercury. And probably Mertis on Bepicolombo will have the opportunity to detect graphite feature in the thermal infrared spectral range. And we try to reproduce experimentally this detection at 600 nanometer, but we could not so far not be successful. But of course, we want to continue with our experiments, and probably there could be some grain size effects, so we want to try again with some finer graphite and probably with other graphite sample, because we don't know if the different graphite may have different behavior. And this is my last slide. I thank you for hosting me to this meeting. Unfortunately, I probably cannot stay online for so much time because I have to prepare dinner, and then my children are coming back home, so I cannot guarantee that I will be there for the remaining of the meeting, but I will take your question. Thank you.
Thank you very much, Alessandro. Do we have any questions from the audience? Yeah. Any yet? Well, I just have one that occurred to me about Mertis on Bepicolombo. I'm really intrigued that it's going to be able to look in the 7 to 14 micron spectral range. Do you offhand know what kind of resolution, spectral resolution, that instrument would obtain?
Yes, I have this on.
I'm sorry if I missed that. I stepped out of the room for a minute.
You mean about Mertis?
Yeah, Mertis. Right.
Yeah, it's 200 nanometers, so it will be very high spectral resolution.
Okay. Oh.
Hey, Alessandro, it's Kathleen. You showed that you have this change in slope when you add carbon to a komatiite. So when you guys get data back from Mertis, are you going to be able to place any constraints on the graphite abundances?
But this is something that we wanted to do. In fact, this is just the starting point, because you see that even few percent of graphite have a very high influence. So what we want to do is we want to decrease the amount of graphite, even reducing to couple percent, 1%, and see if we can see some significant spectral feature or influence. That could be a good point for posing some upper and lower limit of detection that we may have with Mertis on Bepicolombo.
Okay, we have some questions in the box. Could you scroll up? I think there's one before Diane.
That was the one that just got asked, I think.
Okay, we just got that. Okay, then let's do Diane's. Diane Wooden asks, please describe again what you mean by spectral ratio in the lower plots that you showed.
Yes, I was referring to the work by Rachel Klima. So what we did is we just took the graphite plus komatiite spectra, and we ratioed the spectra to the komatiite alone measurement, just to highlight spectral features that are not present. So this is, let's say, standard procedure. You just take a region where you think about you may have some spectral features, and you divide this for a neutral region. So we use the komatiite alone as the neutral mercury or average mercury, and we divided the komatiite plus graphite spectra for that komatiite alone. Is that an answer to your question?
Yes, I think so.
And of course, Rachel Klima did some other operations on using some spectral bands in the MDIS data. We didn't reproduce this because we just tried to see if just rationing we could find something around this 600 nanometer region.
Okay. So I have a question about your grain sizes.
Yeah.
So on your graphite, and maybe you want to scroll back to your slides, but on your graphite, when you saw that perhaps 500 nanometer absorption feature, what was your graphite grain size there?
Yes, this was 50 microns. That's the reason why it could not be maybe accurate for Mercury, and that's the reason why we want to continue this study with some smaller grain size graphite.
Okay. And in your mixtures of komatiite and graphite, where you show that you only need a little bit of graphite to make a big difference, what are your grain sizes there?
So this is our komatiite. It's smaller 25 microns. So it's the smaller grain size that we always consider as the appropriate for Mercury.
25
so
microns?
Sorry?
Did you say 25 microns?
Yeah, smaller 25 microns. So it's, you can say 0.25 microns. And
okay, and then that's with the 50 micron graphite?
Yes.
Okay. And so for those grain sizes, you only need a little bit of graphite to make a big difference.
Exactly.
Got it. Okay, thank you.
Okay, great. Well, I think, oh wait, we've got something from Rachel here. She says,
That's
in the
okay.
work
I
we-
can talk about it when I
Okay, great.
when I do my talk. And yeah.
okay, very good. Yeah, I was going to say in the interest of time, why don't we move on? Thank you very